Algebra 2, Chapter 16, Section 4, Matrices and Systems of Linear Equations. So if we think back and remember about systems of equations, we can write them as like this. We put a brace, which kind of meant a set, and we wrote these equations. And remember, a system of equations meant these three equations have to be true all at the same time in order for there to be a solution. And the solution would be the x, y, and z values that make all of the equations true. Okay, now we can actually write this in matrix form. So all we need to do is write the coefficients in a matrix. So these correspond to these coefficients. We put a 0 if there's no variable, because 0 times a variable will be 0. Then we write our variables in a vector, and that will equal the constants on the right that the equations are equal to in another vector. Okay, so we could think of this sort of as an A matrix. We could think of our vectors of variables and sort of a B vector or C vector for constants. And A times V equals C. So we can write this vector equation or matrix equation that tells us how to find or how that represents the solving all these equations at the same time. Now, if we go back here, we can see these extra parentheses, right? That's the actual form and equal sign. So this sort of setup happens so much because of systems of equations that we actually have a special form of a matrix we use to represent this called the augmented matrix. So in the augmented matrix, we take the matrix A and we write a bar, and then we write the vector C all in one big parenthesis, just like this. And it means just the exact same thing as what we just wrote here, which means the same thing as this set of equations. Okay, so here's our augmented matrix. So an augmented matrix is just a shorthand for the normal matrix form for a system of equations. But what we can do with an augmented matrix is we can solve the system using equivalent operations on rows in order to put the augmented matrix into something called echelon form. An augmented matrix is in echelon form when the lower diagonal matrix is all 0. So all the numbers here. So this augmented matrix is not in echelon form. A matrix that is in echelon form can be easily solved by back substitution, because we would say, so suppose those were 0, then we would know 1 times z equals 0. So that would tell us z equals 0. And we can back substitute to find all of the answers. And this is similar to solving by substitution or elimination, like we studied when we studied systems of equations. So adding or subtracting two equations when we're dealing with echelon form, we just add or subtract two rows. Multiplying an equation by a non-zero constant is the same as multiplying a row by a non-zero constant. And switching the order of the equations, we can just switch the order of the two rows. And of course, their corresponding variables. So if we're keeping track in the augmented matrix, if we switch some rows, we would need to remember to switch the rows in the variable matrix or vector, or you can get confused at the end. So be careful when you're switching rows to remember that little trick. So if I wanted this bottom row to be the first row, I could do that, but I need to swap the x and the z. Here's a systematic way we could put any matrix into echelon form. First, we can start by swapping rows if there's a 0 entry in the top left. And again, if we swap rows, we need to keep track of what we've done to the variables. So you can write that off to the side when you do a row swap. Then add multiples of the top row to all the other rows to get zeros for the other entries in the first column. Okay, so that we'll do examples of this so you'll understand this better, but just this is the general pattern. And then we repeat steps 1 and 2 on the submatrix under and to the right of the first row and first column. So if we think of this augmented matrix here, we don't need to swap anything to get a non-zero here. It already is non-zero. So we would multiply this row and subtract or add to the other rows to make these numbers become 0. Okay? And then after that's done, we work on this submatrix. Okay, and when that's done, we work on whatever's left. Now, all we have to do here is make sure that's not 0. Okay, and if it is 0, we have a problem. We'll talk about that here in a second. Okay, so basically, if you end up getting all zeros for your variables, and you end up with something that's not 0 here, that's like saying 0 equals 3, if that was a 3. If that's a 0, then you'd have something that's always true, and this bottom row would contribute nothing to your system of equations, because it's trivially always true. And if it's always false, then it makes it impossible to solve your system of equations, because one of your equations has no solution. Okay, so that's how we can deal with that. Okay, so let's do some practices here. So suppose that we have this system of equations, 3x. Nah, that one's too easy. Let's do the example I already had. So we'll have 3, 2, 5, 11. 3, 2, 5, 11. 2 minus 3, 1, 7. 2 minus 3, 1, 7. Minus 2, 0, 1, 0. Minus 2, 0, 1, 0. Okay, and our initial order of the variables, write this down on the side just so I keep track if I just do a swap. It's x, y, z. Okay. So the first thing we do is make sure this is not 0, and it's not, so we can keep going. Now we've got to eliminate. Okay, so I'm going to go ahead and write a new augmented matrix below it. I'm not going to do anything to this first row by itself, just leave it alone. Now I need to multiply by a number to make where I can subtract or add to get rid of this. So if I multiply this row by, and I'm going to do some scratch work over here, multiply it by 2/3, I would have 3 times 2/3 is 2, 2 times 2/3 is 4/3, 5 times 2/3 is 10/3, and 11 times 2/3 would be 22/3. Okay, so now I have 2 and 2 by multiplying this row by 2/3. The 3's cancel, we have a 2. So if I subtract this row from these numbers, it's just like subtracting equations, and I can now have a row here that'll have a 0 in the front. So getting a calculator to help me. We would have 3 minus 3, of course, is 0, or 2 minus 2 is 0. That's what we're trying to do. And then we have 2 minus 4 over 3, which the calculator is not much help with fraction math. If we want to keep the numbers exact, we should really subtract 6 from 4 is 2. And that would give us 2/3 left over. And then we have 5 minus 10/3, which is 15 minus 10 for 5/3. And 11 minus 22/3 would be 11 times 3 is 33. So 33/3 is 11. 33 minus 22 leaves us with 11/3. Except I didn't subtract. Hold on now. Did I? I did something wrong here. Let's erase this and try this again. Okay. So here we're taking 2, which is 6/3, and subtracting 4/3. No. We're taking -3. See, I got confused. I was looking at the first row when I'm really working on the second row at this point. Okay. So it might help to have some rulers or some way of keeping track kind of where you are as you go. Okay, so I know I'm working on the red part here. So I did 2 minus 2. Now I have minus 3. So I'm taking this equation and subtracting this one from it, but I multiplied it by 2/3 first. So we have minus 3 minus 4/3. So that would be minus 9 minus 4 minus 13/3. Okay, so we have minus 9 minus 4. We have 1 minus 10 thirds. So that would be 3 thirds. 3 minus 10 is minus 7. And then we have 7 minus 22 thirds. 7 would be 7 times 3 is 21. So you would have 21 minus 22, which is negative 1 third. Okay. Let's make sure this is plain. Okay, I'm more confident we got that part right now. Now, next row, we can reuse these numbers. This time we'll add the row, for first row times 2 thirds. We're going to add that to the third row. Okay, so we have minus 2 plus 2 is 0. 0 plus 4 thirds is 4 thirds. 1 plus 10 thirds is 13 thirds. And 0 plus 22 thirds is 22 thirds. Okay, now we're going to work on the submatrix. Okay, only really need to think about this part now. And all we start with is this number at the top left 0? And if it's not, we don't have to do anything. Okay, now we need to take some constant times this row and add or subtract it from here to get this 4 thirds to be 0. So I need negative 13 thirds to become 4 thirds. So I would need to multiply by 4 thirds over negative 13 thirds. So the negative 13 thirds cancels to 4 thirds. So this will be my multiplication factor. Remember, in complex fractions, I just multiply by the denominator inverted. The 3's will cancel. Leaves us with 4 over negative 4 thirteenths is what I need to multiply this by to get what I need to add to get this to be 0. Okay? This example is kind of rough, but that's okay. We can get through it. So negative 13 thirds times negative 4 thirteenths will be the 4 thirds that we wanted. So when we add, we'll get 0. So let's go ahead and write a new augmented matrix. We're not going to be changing much of it. First 2 rows are going to stay the same. We're going to make this 0. So now it's just these 2 numbers we need to fill in. So 13 thirds, we're going to take 13 thirds and we're subtracting. So 4 thirds minus, well, we didn't even write this part down yet, times. So we want to multiply this row by negative 4 thirteenths. Okay, we do that and we get 4 thirds, negative 7 thirds times negative 4 thirteenths. Okay, it's going to be a positive number, so 7 thirds times 4 thirteenths. And there's nothing in common here, right? 13 is prime, 3 is prime, 7 is prime. 4 is 2 squared, but there's no 2's in the denominator, so this is just going to be multiply the numerators and denominators. 7 times 4 is 28, and 3 times 13 is 26 plus 13, 39. Okay, and this last negative 1 third times 4 thirteenths is going to be negative 4 over 39. And that gives us what we need to subtract from. So now we have 13 thirds, because we're subtracting. We have 4 thirds minus 4 thirds is 0. 13 thirds minus 28 39ths is this number. Okay, so we need to make, we have to multiply by 13 over 13 here to get 39 in the denominator. I think 13 times 13 is 169. Might as well check that. And subtract 28, 141 over 39. Of course, that's not any kind of simple number. 141 over 39. And then here we have 22 thirds minus negative 4 39ths. It's going to be plus. We need to multiply by 13 to get this to be 39ths. So we'll have 22 times 13 plus 4 over 39. 22 times 13 plus 4 over 39, which of course is not a round number, but it's 290 39ths. So now we can back substitute to solve, assuming I got all these numbers right. If I didn't, it's okay. You get the idea of how to do this, I hope, just from me walking through it. So we need to then write the solution. We can write the solution as a vector. So I'm going to erase some of this work here. So our solution vector x, y, z is going to be, so for z we have, this is 141 over 39 times z equals 290 over 39. Okay. And one of the things I just realized that would have made this simpler is, as we're going, we can multiply any row by a constant and it's the same. So we could have multiplied this row by 3 to eliminate the thirds after we gotten to this point, after we'd done our subtractions, and it would have been fine because this still stays 0. So this would have been minus 13, minus 7, minus 1. And that would have made this a little simpler. And we could have done the same with the second row. Maybe we'll try that in a minute just to see how that works out. So here the 39s will cancel. You'll have, and this is z times this, so you have z is 290 over 141. Which is almost 2. So that makes me wonder if I'm off a little bit somewhere in my calculations. 290 over 141. Okay, and now we can take the z value, we know to multiply by negative 7/3 to try to find the y value. So the y value would be minus 13 thirds y will equal minus 1/3. I'm going to go ahead and move the 7/3 over, plus 7/3 times z, which z was 290 over 141 if we got it right. 290 times, let's do 3 times 141, 423. And 290 times 7 over 3 times 141. It's about 4.8. And then we'll add that to 1/3. And that'll give us, when we add to 1/3, 1,889 over 423, which is about 0.48, 4.8. So let's go ahead and just round these off at this point. So 290 over 141 was 2.0567, which we'll write as 2.056. Or really, we'll just do the whole thing. And then 4.7991. Okay. And now we can do the top row will be 3 times x plus 2 times y plus 5 times z is 11. So 11 minus 2 times y, 4.7991, minus 5 times 2.0567 will give us x, 3x divided by 3 is negative 2.96. Negative 2.9606. Okay, so if I got all the numbers right, that would be the right answer. So let's see if I can do this real quick. I need a big eraser, that's what I'm looking for. Okay, so erased all that, so we can start over here. Actually, let's erase this stuff too. Okay, and still have a little bit of stray markings. Okay, so going back to where we were here, if we multiply this by 3, we can wipe these fractions out. We don't need to carry these fractions around, assuming that I hadn't made any mistakes to this point. Okay. And now we multiply by, to go to this last row. So this is much simpler. Let's erase these last two numbers. Would be, we need to multiply by 4 over negative 13. Okay, so that would give us, in order to turn negative 13 into 4. So that would give us, for the second row, we'd have 4, of course, and then negative 7 times that. So we'd have 7 times 4 over 13, and negative 1 times that, so 4 over 13. So we'd be subtracting negative 7. We would take negative 7 and subtract 7 times 4 over 13. So 7 times 4 is 28. So 28 thirteenths. So we'd be taking negative 7 and subtracting 28 thirteenths, which would give us negative 7 times 13 minus 28 thirteenths. Negative 7 times 13 minus 28, negative 119 over 13. Okay, and I'm just going to write the negative 119 because I'm going to end up multiplying this whole thing by 13. Well, we'll just write it for now. Let's not skip anything and make another mistake. And then 22. Oh, see, I made a mistake here. We're taking not negative 7. We're taking... goodness gracious. Let's erase all this. See, everyone can make mistakes. It's part of math. We just need to check our work so we see the problems. We did 4. We're working on this bottom row. 4 times, we're taking this row, multiplying, and then we're going to subtract 4 from it. So we have 4 minus 4, 13 minus 28 over 13 will give us 13 times 13 minus 28 over 13. Okay, so 13, that was 169. That was the number we had before. 141 over 13. And then minus 1, no, now I have 22 in that last row. 22 minus times 13 minus 4 over 13. 282 over 13. And like I was saying, we can now multiply this by 13 and we don't have to deal with that anymore. Okay, so we just have integers here. And 282 over 141 is 2. So see, I did make a mistake somewhere. This was wrong. This is what my hunch was telling me, is that we were slightly off. Okay, so z should be 2. When we take 141z equals 2a2 divided by 141, we get 2. So now that z is 2, we have minus 1 on the right, moving the minus 7 to the right side of the equation, we'd have plus 7 times z, which is 2. Plus 7 times 2. So we have 13 equals negative 13. Divide both sides by negative 13, we get that y is negative 1. And now we have 11 minus 2 times negative 1, which is just plus 2. And then minus 5 times 2 is 3. 3 divided by 3 is 1. And so the solution to our system of equations is 1 minus 1, 2. Now, one of the other cool things about doing this with matrices is that we can check our work with matrix multiplication. So if we take our answer and we de-augment this matrix so that we have the original matrix, 5, 1, 1, and multiply by our solution, we should get the constant vector on the right. And if we do, then we've done the work correctly. So 3 times 1 plus 2 times negative 1 is the same as minus 2 plus 10. This should be 11. And so the first entry is right. 2 times 1 plus negative 3 times negative 1 is 3, plus 2 is 7. And now minus 2 times 1 plus 0 times 1 is 0, plus 2 is 0. And sure enough, it checks out. This is a solution to our system of equations. Okay, so what I told you earlier about having to swap the variables is wrong. I don't know why I was thinking of that. So let's do an example that shows this clearly so that there's no confusion. So let's do example 7 in the book, okay, which will show how to do the swapping step, which we didn't need to do for the first one. So I'm going to go ahead and start by writing this in echelon form. 0, so I'm looking on page 489 of the book, example 7, 16.4. 0, minus 1, 2, and then our bar for augmented matrix 8. 1, 2, minus 1, minus 2, minus 4, minus 1, 1, and 7. And so swapping the rows just means the same thing as, let me go back to the slides here. It means the same thing as just reordering the way we write these equations. So if I swap these equations, I'm not doing anything to the actual variables. I don't need to change the ordering of the variables at all. Okay, that would be true if I was somehow swapping these numbers in the columns, which we're not doing. Okay, so we don't have to worry about that first thing I mentioned about keeping track of X, Y, and Z. I'm sorry about confusing you. So to swap a row, we just do it. So let's swap. The book swaps the first and last. Let's swap the first and second and see if we get the same answer. Okay. We should, because it shouldn't matter. 1, 2, minus 1, minus 2, 0, minus 1, 2, 8, minus 4, minus 1, 1, 7. Okay, and now we've already got, this is a 0 for our echelon form. Okay. Now this time I'm going to do something a little different. Instead of multiplying over here a new row, I'm just going to take, since I only need to do this row by one thing, I'm just going to multiply this whole row by 4 right in place. So 4, 8, minus 4, minus 8. And that doesn't change anything. It's just like multiplying the equation by 4. Okay, now I can add, I'm going to draw a new one now so we don't get lost. 4, 8, minus 4, minus 8, 8, 7, 2, 1, minus 1, minus 1, 0. Oh, I don't want to write the bottom row. Now we're going to take the first row and the last row and add them. So 4 plus minus 4 is 0. 8 plus negative 1 is 7. Minus 4 plus 1 is minus 3. Minus 8 plus 7 is minus 1. Okay, now we've got those two zeros. We just need to look at this bottom matrix, submatrix, which already has a non-zero thing here. Don't need to worry about swapping in this time. But swapping was super easy, so it wasn't hard. I'm sorry about confusion there. 0 minus, okay, so I'm going to take the second row and multiply by 7. Minus 7, 14, and 7 times 8 is 56, or is it 50? Let's make sure of that. I'm pretty sure that's right, but you know, multiplication tables were a long time ago for me. Yay, I still remember my multiplication tables. 56, okay, so then we have this bottom row, 0, 7, minus 3, minus 1. Now let's add those two rows to eliminate the 7 in the bottom row, and that'll give us a matrix, an augmented matrix in echelon form. 0 plus 0 is 0, minus 7 plus 7 is 0, 14 plus negative 3 is 11, 56 plus negative 1 is 55. So Z would be 55 divided by 11 is 5. Sure enough, is that what's in the book for example 7? Yes. Then Y, we can take 56 minus 14 times 5 divided by negative 7 and get Y is 2. and x is minus 8 times the y value of 2, plus is negative 4, plus 4 times 5 gives me minus 4 divided by 4 is negative 1. Okay, now we can check. Always like to check. So going back to the original matrix for checking, you could check against this matrix. It should also work if we made no mistakes. But assuming we didn't copy the first matrix wrong, that's the way we want to check from to make sure we didn't make a mistake in between. Okay, this better equal this original vector to be correct. So we have, and with a 0 we can forget about the first thing. Minus 1 times 2 is minus 2. Negative 2 plus 10 is negative, sorry, make sure I did this right. Negative 2 plus 10 is 8, okay? That matches, good. So far so good. 1 times negative 1, minus 1 plus 4 minus 5 is negative 2. Good. So far so good. And this better be, was it 7? Minus 4 times minus 1 is 4. Minus 2 plus 5, 7. Checks out.